Alright, hello class. In this video we're going to be talking about the cross product, and this will finish off the overall vector basics, vector arithmetic, and let us move on to actually start talking about calculus in this stuff. Alright, how do we apply this in a way that starts to approach those ideas I was talking about before with the different independent and dependent variable combinations. Okay, so first of all, we'll talk about the cross product, and this is our final version of vector multiplication. All right, so as I mentioned a few times now, there is no just straight up vector multiplication. So it should be more vector multiplications because there's different ways we can talk about multiplication in terms of vectors. The first we talked about, which is scalar multiplication. That's where we take a scalar, multiply it by a vector, and we get a new vector. And this is a scaled vector. Right? So this scales the magnitude. Right, but leaves the direction unchanged. Okay. Then in the last video, we talked about the dot product, which does take a vector and a vector, but it spits out a scalar. And what this does is it measures how much push one vector gives to another. Okay, and the last one we're going to talk about is the cross product. Now this one is a lot closer to normal multiplication than what we've seen before. So here we have two different things, a scalar and a vector, giving us a vector. Here we do have two vectors, but it spits out a scalar, not a vector. In this case, we do take two vectors, so a vector times a vector, and we get a vector. Okay. However, there is some funkiness to it that makes it not 100% how we usually think about multiplication. Okay, so let's talk about what the cross product is, what it gives us, why we want to talk about it. All right, so given two vectors, v and w, the cross product, which we call v cross w, so we use the x form of the multiplication, gives us a vector. So I'll say gives us a specific vector that is perpendicular to both v and w. Okay, so the first question I think that pops up is, well, what direction are we talking about? Right? Because if you have two vectors, say a v and a w, there are going to be two vectors that are perpendicular to both. We have one, well, I'll say two directions that are perpendicular to both. Right? So we would have one that, say, points up away from v and w, and one that will point, say, down. Okay? So, for example, if you think of the vector I and j. Right, so this is the vector corresponding with the x-axis, this is the vector corresponding with the y-axis. We have two directions that are going to be perpendicular to both. We have the positive z and the negative z. Okay, so which one does the cross product give us? Okay, and then once we have the direction, so we'll start the first question is which direction? Okay, and then the next question is what's the magnitude? All right, so to answer the direction question is what we say is that the cross product satisfies the right-hand rule. Okay, and the right-hand rule, it's kind of difficult to talk about in terms of this stuff without you seeing my hands. Okay, but I'll do the best I can. What the right-hand rule means that if you're doing F cross, or sorry, not F, but V cross W, you're going to look at the vector V and the vector W. For example, here's say a V and a W. And what you want to do is, I always like to take my right hand and karate chop the first vector, V. Okay, so you're going to take your right hand, sorry lefties, you're left out of this, and you're going to karate chop it and then curl your fingers towards the other angle, or not other angle, but as if you were making the angle between them, the smallest angle between them, with your by curling your fingers. And when you do that, your thumb is going to be pointing in the direction that would be the natural cross product. Okay, so that means your V cross W is going to be pointing in this direction because you are going this way. You can karate chop the V and curl around with your right hand this way. However, if you did it the other way, W cross V, right? So W cross V means we're going in the other direction, W to V. I can't karate chop it in the same way because if I were to karate chop W with the thumb pointing up, I can't curl my hands that way. I would be curling my hands, my fingers this way, which is the wrong orientation. So I'd basically be talking about the wrong angle, right? So in order to do it, I'd have to flip my hand around the other way, right, upside down. So that I could curl my fingers this way. And so my thumb in this case would be pointing down instead. All right, so the implementation of this isn't as important as what it means for us at the end. So, okay, so the important part is in practice, if I do I cross J, okay, so I'm doing I to J. It's sort of similar to here. The vector that pops up, we want to be K. And if we go in the opposite direction, say J cross I, we want to get out negative K. Okay, so how I like to think about it is if you draw your vectors on the XY plane, right? So if you think about it in terms of here's I and here's J, just pretend, if we're looking down on the XY plane, the positive z-axis is pointing towards us. So if we are going with a positive angle, right, this would be a positive theta, we get a positive K. If we go in the opposite direction, right, if we go counterclockwise, a negative theta will give us a negative K. Okay, so there are a lot of different ways we can think about this, but this right here, that I cross j is equal to k, is where we build everything from, okay? Because just from the that idea that we're satisfying the right-hand rule, and we want the unit vectors to cross with each other and give us unit vectors. All right, so before we start talking about the magnitude, if we think about like k cross or j cross k, we think about it in terms of the right-hand rule, our thumb should be pointing towards I, because if we want to curl our fingers around to go from j to k, it's going to be pointing towards the positive I. Okay, then if we want to do k cross, use a different color here. If we want to do k cross I, right, so we're going from k down to I, well, we can, if we're using the right-hand rule, our thumb should be pointing towards j, because if I want to naturally curl my fingers around using my right hand always, my thumb will be pointing to j. Okay, so these are the three important guys we're going to use. You just have to remember that if you swap the order, you get the negative value. So that's the big thing, that v cross w is negative w cross v and vice versa. When you swap the order, all you do is swap out, throw in a negative, you negate it, you oppose the direction. Okay, now to answer the question about magnitude, all we really need to do is note that it just carries over scalars. So scalars carry over, so that 2i cross, let's say 3j, okay, well, that's going to be, I could just bring the scalars together and get 6 times I cross j, so it will be 6k. Okay. So if we wanted to look at that visually, here's 2i, 3j, and then the magnitude of the cross product will be these lengths multiplied together, which will be 6k. And it turns out that this rectangle we made here, and later it will be parallelograms. This is a 2 by 3 parallelogram here. This area is 6, which happens to match the area of, or not the area, but it happens to match the length of the cross product. Okay, so it turns out that the area of the parallelogram formed from the two vectors that we're crossing equals the length of the cross product vector that we get. I'll write down. Okay, so first let's distribute the Vx term across. And you do it just like you would in algebra, and this is finally the answer to that question. So we're going to have Vxi cross Wxi. Now you might be thinking, we didn't really talk about what I cross I was. Okay, well, how many vectors are perpendicular to both I and I? Well, it turns out there's tons that are perpendicular to I, including j and k and anything on the the YZ plane. But if we go back to this area argument, that the cross product's length needs to equal the area of the parallelogram, well, there is no parallelogram. So it turns out that I cross I is 0. So this whole piece here goes away. That's 0. Okay? Then it will be plus Vxi cross Wyj. Okay? Then it will be plus Vxi cross Wzk. And I'm going to write these out. Right, so next I'll expand out the second term, and then I'll do the third term, and I'll spare you from watching me do every little step. I'll come back when it's all said. All right, now that I've expanded this all out, any matching thing is going to be 0. So I cross I is 0, J cross J is 0, K cross K is 0. So this one that gives us the J cross J is 0, and this one that gives us the K cross K is 0. Right? So those guys disappear, and now we're going to replace a lot of these things with what they end up being. Like I cross J, that's K. So we're going to get Vx, Vy, K. Right? So that's what that comes out to be. Next up, okay, and over here I've put what we had before. I just moved that to here, so we can have it all on one screen here. Then we have the I cross K. So I cross K. Well, K cross I is J. That means I cross K is negative J. So this is actually going to be negative Vx Wz J. Okay, so whenever the order is opposite, so order here really matters, we throw in a negative. Okay, so that would be this piece. Then next I have J cross I. Well, J cross I, that should be negative K. So you'll get negative Vy Wx times K. So that will be this piece taken care of. Then that disappeared, so now I have Vyj cross Wzk. J cross K is I, so this will become plus Vy J cross K is I. So, whoops, be Vy Wz I. So there we go, there's that piece. Then moving down along here, K cross I, so I'll get Vz Wx, and then it will be K cross I, which K cross I is J. So that's that piece. Notice I have two J pieces here. And I probably should have used the same here for the K's, the two K's in blue. And then we should have one last piece here. The K cross J, that's going to be a negative I when we do that. So it'll be negative Vz Wy, whoops, Kj, which will be I. So we'll mark that in yellow. Okay, so I tried to mark the matching matching letters in matching colors. Alright, so now I've combined all my like terms and kind of put it in a simplified way. I will note there was a typo here. That should be here. That should be a WY, not VX, VY, VX, WY. if I didn't remember to fix that in the editing software. There was a bit of a typo there. But anyway, this is what we get down to. Our V cross W, right, ends up being VYWZ minus VZWY I plus VZWX minus VXWZJ plus VXWY minus VYWXK. Now, in general, this is not something I would recommend just memorizing. Okay, so this is the pattern, and you'll notice that like we have in the I component, we only are looking at the Y and Z stuff. We're not looking at the X stuff. In the Y component, we're only looking at the Z and X stuff. We're not looking at the Y stuff. And here in K, we're only looking at the X and Y stuff, none of the Z stuff. Okay, but we can kind of see a bit of a pattern going on. But it's sort of like, well, what pattern is this coming from? And it turns out that we can use a trick from linear algebra to help us out, so we don't have to memorize this, right? And that trick is the determinant. We make a matrix and calculate. Now, if you don't know what a determinant is, if you haven't taken linear algebra, don't worry about it. If you have, you're already ahead of the curve. If you've already learned how to do this, you're already ahead of the curve. But if you aren't, don't worry about it too much. Here's what you need to know. If you have a 2x2 matrix, right, say A, B, C, D, the determinant is you take the main diagonal, multiply them together. Then you take the minor or opposite diagonal and subtract, right? So the determinant of a 2x2 matrix ABCD is AD minus BC. Okay, great. Now, with a 3x3, there's a lot of ways to do this, okay? Every time I teach this, a student will always ask, oh, I learned how to do this way. Is that okay? Yes. All right. As long as you get the right answer. I'm just showing you what I feel to be the most straightforward, quickest way to do it with the least amount of opportunities to make mistakes. Okay. So here's how I do this. So to calculate, all right, the cross product, V cross W, I set up a 3x3 matrix in the following way. I do I, J, K in the top row. Okay. Then in the second row, I do Vx, Vy, and Vz. And in the third row, I do Wx, Wy, WZ. And yes, it does matter what order you do this in. This always goes on top, your V sits in the middle, and your W sits on the bottom. Okay? If you swap V and W, you're going to get the negative of your answer. There are ways you can swap this around, but I don't recommend it. Now, from here, I'm going to copy the first two columns again. So I, V, X, W, X, and J, V, Y, W, Y. Now we don't really need the I and J here, really, but it doesn't hurt to put it either. Now, what we're going to do is this same pattern that our normal determinant uses, but we're just going to go through in the following way. I'm going to start with I, okay? And what I'm going to do with I is completely ignore its column, and then shift over one and do the determinant in this 2x2 matrix right here. Right, we make a little box. So it's going to be Vy times Wz minus Vz Wy. Okay, so that's the I. To do the J part, now I just shift over. Right, so once I'm done there, I shift over, and then for the J, I ignore its column, and then I make or calculate the 2x2 determinant of this matrix. Right, so we have its main diagonal, which is Vz Wx minus Vx Wz. All right, then we shift over again, and when I do the K, I ignore its column, and then I do the determinant in the one right next door. So it will be Vx Wy minus Vy Wx. Now, if we compare this to what we got before, okay, which I've dropped right here, copied and pasted it, you can see that we get the exact same pattern that we did before, okay, without having to go through that slog. All right, so I think that this is the quickest way to do it. There are a lot of ways, you know, to go about doing this. If you've taken linear algebra, you've probably seen a bunch of them. This is just, I think, the quickest way, and you don't have to worry about introducing negative signs in different places. It just comes along as part of the process. Okay, so let's look at an example with some numbers in it, and we'll go from there. All right, so let's say I want to find the cross product of V, which is 2, 2, 0, and W, which is 0, 1, negative 3. Okay, so V cross W. So I'm going to set up the cross product calculating matrix here. Right, so I'll have I, J, K in my top row. Then we'll copy down V, so we get 2, 2, 0, 0, 1, negative 3. And then we'll copy down the first two columns again. And you don't really have to do, like I said, you don't really have to do this part, but it, you know, it doesn't hurt. All right, so we'll start with I. So again, we ignore its column, and then we do the main diagonal and the opposite diagonal of what's sitting here. So it'll be 2 times negative 3, so we'll get negative 6, minus 0 times 1, which is 0. Okay? Now, with our J, I'm going to ignore its column and take the determinant of this 2 by 2 matrix. So we'll have J, and we'll have the main diagonal is 0 minus the opposite diagonal, which is 2 times negative 3, which is a negative 6. So this is one thing that we have to be careful about, is that there's quite a few negative signs flying around. Okay. All right, so there's our J, and then we'll do the K, which will be main diagonal, opposite diagonal, so it will be 2 minus the opposite diagonal, which in this case will be 0. All right, so we get the vector negative 6i, negative, negative, so plus 6j plus 2k. In other words, this is the vector negative 6, 6, 2. Okay, let's take a look at this on a graph and see if it sort of lines up with what we expect. All right, so on the graph, here's our v, the vector 2, 2, 0, and as we can see, it's sitting right on the xy plane. Okay, and then we have the vector w, which is 0, 1, negative 3. So this one doesn't go into the x direction at all. It does go into the y and the negative z. Okay, and here is the cross product. All right, so here we go. Here's the vector that is perpendicular to both of them. So that does look fairly accurate. And the magnitude is fairly large, but however, the area of the perpendicular parallelogram made between these two vectors would also be fairly large. Okay, so that does seem to add up. All right, so here it is as promised. Formally, the magnitude of V cross W is equivalent to the area of the parallelogram constructed from V and W. Right, so when we have V, we have W. Okay. The two of them together make a parallelogram. Well, their cross product, which in this case, V cross W, the magnitude is the same as the area. Now notice the units aren't the same because the magnitude of a vector is, say, in meters. Well, the area of a parallelogram is in meters squared. So the units aren't the same, but the numbers are the same. And from this little, because of this, based on, the area of parallelograms and all of that, it turns out that this magnitude we can also relate to the angle between these two vectors. And it's in terms of sine. All right, so the magnitude of the cross product is going to be the magnitude of V times the magnitude of W times sine of theta. Right, and that basically just comes from the fact that if you just look at V and W, the area of a parallelogram is base times height, and you can get this height here. Well, the base is, of course, the magnitude of W, and the height you can get from sine, right? The side opposite and the hypotenuse. So that's where we get this connection. So it turns out that if we have cosine here, that's related to the dot product. When we have sine here, it's actually related to the cross product, specifically the magnitude of the cross product. All right, let's do another cross product problem here. Say 2, 1, 2, and negative 1, 4, negative 2. Okay, so we'll start with our setup. V cross W. It's going to be I, J, K. And now I'll copy V down, 2, 1, 2. And I'll copy W down, negative 1, 4, negative 2. Then we will rewrite the first two columns and we'll get rolling. Okay, so for I, again, we always ignore its own column and do plus the main diagonal minus the opposite. Well, in this case, the main diagonal will give us negative 2 minus the opposite diagonal, which is 8. Okay, and we'll move on to the next one, which is J. We'll ignore its column and do the determinant over here. So it'll be 2 times negative 1, which is negative 2, minus 2 times negative 2, which is a negative 4. Okay. Now we'll move on to the K, which will be the main diagonal, 2 times 4, which will be 8, minus the opposite diagonal, 1 times -1, which will be -1. All right, so we'll get -2 minus 8, so -10i. Here I'll have -2 plus 4, so it'll be plus 2j. And then here, 8 plus 1, which will be 9k. All right, which is also known as the vector -10, 2, 9. So looking on the graph, here's our v, 2, 1, 2. Here's our vector w, -1, 4, -2. And then when we look at the cross product, we see it definitely is a vector that is perpendicular to both and is satisfying the right-hand rule. We do have to zoom out a bit to see the whole cross product, okay? But there we go. All right, now it looks like this trick works. Let's actually double check just to make sure that when we do I cross j, we actually get out k. Okay, so that's going to be 1, 0, 0 cross 0, 1, 0. So taking this cross product, I'll do I, j, k, and then 1, 0, 0, 0, 1, 0. And then I'll copy down the first 2 columns. Now this should go fairly quickly because we have so many zeros, right? For the I, the main diagonal is 0. The opposite diagonal is 0. Okay. So then for j, once again, the main diagonal is 0. The opposite diagonal is 0. And I put I there. And for k, well, that's where we should get the only thing, and we do. Here we get 1 on the main diagonal and 0 on the opposite. So this comes out to just be k, okay, or 0, 0, 1 as expected. And I actually recommend that you go back and do each one of these reversed just to make sure that you get the negative of what we got here. Okay, one major physical application of the cross product is torque. So if, say, you have a bolt, all right, and you have a wrench, or you've got like a socket, something like that, and you apply force to the wrench, it turns out that the torque applied is perpendicular to both the force and the wrench itself, satisfying the right-hand rule. And it turns out that that torque is equal to the cross product, right? So if you represent, so if R represents the length of the wrench, and F is the force applied to the wrench, okay, then the torque, okay, is the force applied to the bolt, all right, and its magnitude is given by F cross R, its magnitude, which will also be the magnitude of F and R multiplied together times sine of theta, and we always want theta between 0 and pi. Okay, and torque is actually represented as the vector V cross R. It's actually the cross product. So what that actually means for us is that if we're following the right-hand rule, so how we typically do this is we think about R as a vector pointing away from the bolt itself. Okay, and if the force is acting here, we often redraw it over here. Okay, so and I just did this in the opposite order. Sorry, the torque is actually R cross F. Right, so if you're following the right-hand rule of this angle between them, right, so if you're twisting the wrench in a positive orientation, it's going to be applying force upwards this way. However, if you flip around and do your force in the opposite direction, you will get a downward force, or in the opposite direction. I mean, hopefully that's intuitive to everyone, because if you've ever used a wrench before, you know that if you push it one way, you're going to unscrew the bolt. If you do it the other way, you're going to screw in the bolt. Right? If you think about a socket wrench, you set it to one direction, and what's happening is one direction is tightening, the other is loosening. So this is our tightening versus loosening. Right? And it has everything to do with what direction that you are pushing the wrench at. All right, so let's say here's our R, here's our F, and here's our torque vector. All right, so I want to take a closer look at this particular formula here, and I find this really interesting and actually kind of intuitive. The magnitude of the torque, the amount of torque you get, is completely determined by, well, the magnitude of the force. Okay, that makes sense. If you increase the force, like here, you should get more torque, right? If you put more force on the wrench, you should get more force out of it. It's also determined by the angle, right? If you are making a 0-degree angle with the wrench, either this way or, you know, if you're parallel to the wrench, you're not going to do much. One, you're going to pull it away. Another, you're just pushing into it. You're not actually twisting the wrench. Okay? So, and what's interesting, I find, is that, say if you are at something like pi over 6, right? If you're at 30 degrees, so actually let me clean this up a little bit. Say you're at like 30 degrees, right? Or here. Sine of pi over 6 is just 0.5. Versus if you come at it at a 90-degree angle, let me do that in, looks like that's what I have here. When you come at it at a 90-degree angle, sine of pi over 2 is 1. So at 30 degrees, this factor here is only 1. But at 90 degrees, oh, sorry. If you're at 30 degrees, this guy is only 0.5, but when you're at 90 degrees, it's at 1. So at 90 degrees, you get the most torque versus hitting it at other angles. Then finally, and you may have seen this before, R. If we increase R, lengthening the wrench will also give us more torque. And you may have seen that. I've seen it before, old timers when they're working on cars or something. If the wrench isn't giving them enough torque to unscrew a bolt, I've seen them take a pipe, like a longer pipe, and put it around the handle of the wrench and then use the end of the pipe, which lets them break that bolt off. That's giving them more torque because they can't increase the force that they're applying. All right, they can change the angle, but that's kind of hard to... Usually you are applying it at 90 degrees, but if you can't increase your force by anything, you increase your length. So we can see it right here in the math, right? That the torque is completely determined by the force you apply on the wrench, of course, the angle at which you apply that force, makes sense, and the length of the wrench itself. Okay? So, as far as the math goes, it's exactly like what we've been seeing before. You would just, take the cross product of these two forces, or not the two forces, but the force and the length of the wrench, and that will give you your torque. Okay, so I think that's enough for this particular video. In the next one, we'll start actually getting into how we can actually apply calculus to vectors. Okay, and I will talk to you all in that one. Cheers.